Thank you very much. So yes, we are going to talk about the idea of a cloud-native compiler, JIT-as-a-Service. Now, before we get into the idea of what we do in terms of that cloud-native compiler, we need to provide some background in terms of why you would want to do this. Now, the first thing is, if you're using a JVM-based application, so it could be Java, could be Kotlin, could be Scala, any of the languages that can compile the point codes, that's really good because Java and the JVM have been very, very popular for the last nearly 30 years. But what we find is the way that that works is very good for scaling, is very good for being able to run cross-platform and write once, run anywhere. But there are certain things about how that happens that are very important when we think about deploying into a cloud environment. And again, if we go into a little bit of background on this, what we do when we run let's call it a Java application, is we run bytecodes. Bytecodes are these instructions for a virtual machine. So we've got the Java virtual machine. And because they're for a virtual machine, they have to be converted into instructions for the platform that we're actually running on, whatever cloud instance we have set up. And the way that we do that is in a number of different stages. So initially, they are interpreted, meaning that we take each bytecode in turn and we convert it directly into a set of native instructions through a set of templates. Those are generated when you start the JVM initially, each set of templates created whichever machine we're running on. So that runs very slowly. And then what we do is we compile them using just-in-time compilation. We figure out where methods being called frequently, we keep account of that, we profile, and then when we hit a certain threshold, we go, okay, rather than interpreting bytecodes, let's compile that code using our just-in-time compiler, and we'll generate native instructions. And we do that in two stages. First is using the compiler, which is very originally called C1, and that will compile code very quickly, generate some native code. We then profile how that application code is being used, and when we hit another threshold, we will then pass it to another very originally named compiler called C2. And what that does is then use the profiling data and recompile that code with much more optimizations in it. So this is a process that we go through when we start up a Java application. Now what that leads to is a performance graph when we're talking about purely the performance of our application that looks a lot like this. It's a very typical kind of graph that we're going to see, where we're starting off slow because we're interpreting our bytecodes. You go through this process of compiling different methods until we reach a point where we've compiled all of the frequently used methods and we've recompiled them with our C2 optimizing compiler, and we've got that optimum level of performance for everything that we're running. And that's what we call application warm-up time, something that everybody who's used JVM, everybody who's run Java code is going to be aware of. Now, the thing about that is that it works very well for, a Java application. What you'll do is you'll start your Java application with Azul, you get your performance level when it's warmed up. But when we start thinking about this in terms of the cloud, we run into a bit of a problem because all of the JVM that we're going to use in terms of microservices are isolated. Even the services themselves are, very tightly coupled in terms of how they operate together, and they have knowledge of different services being used. The JVMs underneath have no knowledge of other JVMs that are being used to run other services or even other instances of the same service. They're completely isolated. They're reliant on whatever resources we provide to them. So the containers they're running in will have a certain number of vCores, it will have a certain amount of memory allocated to it, and that's all you've got to work with. So that's a limitation. And if we look at our microservice-based architecture, when we think about how that works, what we've got is, in this very simple example here, the idea of a number of services that we're going to link together in the cloud. Our client, our customer, wants to interact with that, so they're going to interact with the front end part of that. They'll send some kind of request to have a transaction process. That's going to involve a number of different microservices in terms of what we're doing within our application, and obviously we've got some databases involved as well. The great thing about microservices is that if we get a point where one of our services is being very heavily utilized and it becomes a bottleneck in terms of what we're actually doing, then rather than in a monolithic application where the only thing we can do to improve performance is to throw more resources at the whole application, the whole monolith, what we can do, obviously, in a microservice architecture is simply say, well, that particular service is providing a bottleneck. We need to reduce the load on that. We'll do that by creating more instances of it. We can then do load balancing. We can use things like Kubernetes to figure out how to load balance across the multiple instances we have, so that each of those instances of our service then reduces its load and is able to cope with the increased load that we have across the whole system. So it's a really good flexible architecture in terms of how we can do that. But then we have to think about how JVMs are going to work in the cloud. Now we've got a different situation. Rather than before where we run an application as a monolith, and we run single application in our data center, maybe a web server, app server, something like that. What we now have to think about is the fact that we are not in the cloud. And the cloud we can think of as being almost limitless in terms of the resources that we can draw on. All we have to do is think to ourselves, yes, I will start up a new instance service, provision a new cloud instance, load the application, load the service, get it running, and off we go. We can do that very dynamically. So we can spin up new instances and services, we can shut them down, and we can do that so that we can minimize the cost associated with our cloud fill. What we really want to do, though, is to have the JVM be aware of that. It's not just about thinking at the application level, where we're thinking, right, spin up new services, spin down services. We need the JVMs to be aware of the fact that it can draw on more resources, not just the ones that we have within the container that we're running this particular service in. And there are a number of things that we can do which will improve the whole way that these linked JVMs and linked application services will work. So this is where we come into the idea of a cloud-native JVM. Different to the idea of the JVMs that we've used in the past. It has all the same functionality that your normal JVM has. But what we can do is outsource some of the work that that JVM have to do into the cloud. And we can have something in there, which is what we're talking about in terms of the cloud data compiler, so that it can take advantage of that to reduce the load that it has on the JVM itself and require less resources, be able to process more transactions, and deliver more value, if you like, in terms of how it's running in the cloud. If we look at the basic ideas in JVM, we won't go into all the details of this, but essentially this is what we're dealing with here. JVM consists of a number of different parts that give us a managed runtime environment. At the top, we've got the idea of the fast loader subsystem, what we do in terms of loading passes that we need to run our application. We've got all the verification of those passes to ensure that we don't have malicious code being tried to execute. Then we've got our runtime area. We've got the idea of the heap. We've got the idea of the stack, native memory, method area, and so on. All that managed by JVM. And then we've got the actual execution engine itself. And that will be the interpreter, as I said, creating a set of templates called the bytecodes. We've got the garbage collector that will handle automatic memory management and reclaiming space in the heap as we no longer need it. We've got JNI, Java native method interface, and so on. And we've got this big thing, the JIT compiler, the just-in-time compiler. So it's very logical to focus on that. It doesn't really make much sense to try and outsource garbage collection because the heap is local to the JVM, it's specific to the JVM. We're not going to be able to share a heap amongst multiple JVMs in this particular example. But JIT compilation, definitely something we need to take and we can outsource because we've got the unity methods that we want to compile. We can pass those around and we can compile those in turn compiled code. So let's talk a little bit more about how JIT compilation works, and why we would want to make sure that we can use that in the best possible way. Essentially, what the JVM is doing is saying, here's the piece of code which I want to make better. Now that's a method, and initially that's going to be the idea we've got a set of point codes that represent what that method does. We then want to make that better in terms of compiling with C1 to generate some late instructions. We'll profile that, and then we take that same method and we pass it again to make it even better. So we've optimized it based on what we know about what the method is doing, and therefore generate code. Now the way that works is that the JIT compiler is going to ask a series of questions to the JVM in terms of how is this piece of code being used. It needs to understand the profiling data to say what particular aspects of that method are being exercised, how is it working, and therefore optimize based on that information. The JIT compiler will use that, and then it will eventually return a piece of code that is generated and say, here's the code for your particular situation. JVM will then replace what it's using currently, whether it's set flight codes, whether it's C1 compile code, C2 compile code, or even C2 compile code to something else. And it will say, hopefully that's going to give us better results. And that's all currently done with the JIT compiler that sits inside the JVM. So the other thing that we need to understand in terms of how these things work is about speculative optimizations, because this is really key to how we get better performance and faster speed out of Java. A lot of people, when you talk to them about an idea of JIT compilation and improving the startup time, improving the performance of Java, they'll often say, well, doesn't it just make more sense to compile ahead of time? Why don't we just use the same idea that we have static compilation with C and C++, other languages, and take our Java code, compile it directly to native instructions for that platform, and then run it in the same way. And yes, that will certainly solve some issues, but it doesn't give you the best possible performance. Speculative optimization are really the key to that. So let's talk a little bit more about that. Here's a couple of examples of how we can do these speculative optimizations and how they will deliver better performance, but only if you're compiling as the application runs. What I've got here is a very simple class called animal. It is encapsulating some data, in this case the color of the animal. Very common kind of thing we do in Java. It's object-oriented, so it's encapsulation. We create our class, we put a instance field here for the color, and then because it's private, we need an accessor method called getColor. All that does is return color. All good. Now we can use that in our code, and we can say my color equals animal.getColor. Great. The problem with that is that if we compile that code, even into native instructions, what's going to happen there is, because we're calling a method, the compiler will have to generate a stack frame. Generate a stack frame, push it onto the stack to call the getColor method. GetColor will then retrieve the value of color from that object and return it to the caller. It will then pop off the stack frame. That's very, very inefficient, because all we're doing is accessing a single instance field. The compiler knows about these things. The compiler writer, I should say, knows about these things. So what will happen in reality is that the compiler will say, even though you've made color private, so it's encapsulated, we'll treat it as if it's public. And therefore, we don't have to call the methods to get access to that. We don't have to create stack frame, pop the stack frame off. We can just reference it directly in terms of the compiled code, which is good, because that's much more efficient. The problem with that is that that only works if you only have one version of getColor. This is what it's called a monomorphic site. In Java, you can have dynamically loaded classes. At runtime, you can do class loader, which means that at runtime, you replace the animal method for the animal class with something that does something different. And that could result in getColor doing something which is much more complicated with simply returning the variable. Because of that, if we try and do static compilation, we can't inline that call, because we can't guarantee that somebody won't do some class loading at runtime and therefore result in with a different method being called. We'd only do this if we know as a back we only have one implementation of get color. Give you another example. This is what's called branch analysis. Slightly more complicated method, and a slightly contrived example, but very good to demonstrate exactly how powerful this idea of speculative optimizations is. What we're doing here is saying, okay, method is compute magnitude, it takes a value which is an integer, and then we're doing a test on that value. We say if the value is greater than 9, we are going to calculate a bias. And we do that by calling a compute bias method, pass in the value as a parameter. If the value is not greater than 9, we simply set the bias to be 1, fixed value. And then what we're going to return is the log place 10 of bias plus 99. I said it was a slightly contrived example. What the compiler will do is, as we're running our code, it will maintain a count of how many times we go through each branch of the if statement. So we'll know how many times we've been through the true branch, how many times we've been through false branch. When we come to compile that, as the application is running, the compiler can look at those values, and if we have a situation where the number of times we've been through the true branch is 0, so we've never gone through the true branch, then the compiler can say, let's assume that that will continue in the future. Let's make a speculative assumption about the way this code is working. Up until now, we've never gone through the true branch, so let's assume in the future it's not going to go through the true branch. And the compiler can then change that code completely to improve the performance with that assumption in mind. What it will actually compile is something like this. And it will say, okay, we've got our compute magnitude method, takes a value here. We still need to have the ability to deal with a situation where we do get a value that's greater than 9. In this case, rather than doing what we said to do, we'll call this thing called uncommon trap. The reason we call uncommon trap is because the code that we're compiling is based on that assumption that value is never greater than 9. If we do get a value greater than 9, that breaks the assumption, and therefore we'd have to throw away the code that we've compiled. This is what we call de-optimization. We've made the assumption, we've compiled code based on that, turns out our assumption is wrong, so we have to go back and recompile it in order to respect the contract you have between the developer and the compiler. However, if we don't ever have a value that's greater than 9, what we can do is optimize that code by saying, well, we know that the bias is going to be 1, we know that 1 plus 99 is 100, log place 10 of 100 is 2, so let's avoid all of that extra work and simply return 2 every time. So this is obviously much more efficient, but again, relies on us being able to see what's happening as the application is running. So if we look at our graph again of the sort of overall performance that we get for the application as it warms up, what we're seeing there on the graph is some dips in the performance. And those dips are a result of a de-optimization. We've had to throw away code, revert back to either Python codes, interpretation, or even going back to C1 code, and then recompiling based on new assumptions about how the code is working. What we can then do is we can create like a package, if you like. The package is the method that we want to compile, but also including the set of assumptions that are correct for the compiled code that we generate. So in the example we could have a method that's being compiled based on the idea that there's only one version of getColor and the value that we're processing is less than 10. Now, the other thing that we need to think about in terms of how we can get performance for the JVM is thinking about how to improve performance. How could we raise the level of the optimizations that we're getting? And we can do that by providing better optimizations. If you know anything about like C compilers, for example, and you've used GNU-C or CLang, things like that, you'll know that there are different optimization levels that you can specify when you compile code. And that will, to some extent, dictate how long it takes to compile your code. So let's talk about how we can actually improve optimizations. Here's a simple piece of code. Now what we're doing here is we're taking two arrays of integers and we want to process them in such a way that we're going to add the value of the second array to the value of the first array, but only if the first array's value is even. If we look at that code, it's quite simple. We've got a for loop, we've got if statement C, we've got an even value in the first element of the array, or second element of the array intake, and then we add the second element to the first element. The thing about this is that if you hand that to the JIT compiler in hotspot JVM, it's not going to be able to take advantage of some of the underlying architecture of the machine. We have these things called complexer operations, very wide registers that you can populate with multiple elements of an array, and then you can apply the same operation to all of those elements in a single Fox cycle. So if we look at the kind of code that's going to be generated by the hotspot C2 JIT compiler, this is the type of thing you're going to see. Don't worry about all the individual instructions. What's really relevant here is the highlighting that I've done with the red foxes. So the big red fox represents the body of the for loop. That's where we're doing processing of all these different elements. And the two smaller red foxes represent that the only optimization that the C2 JIT compiler has been able to do is to do loop unrolling. Loop unrolling is a very common technique to try and improve performance by not having to do as many iterations of the loop, because you do multiple elements in each iteration. Azul have a different JIT compiler that we've created. It's called the Falcon JIT compiler. It's based on an open source project in LLVM. Been around for a long time, and it's designed to generate more heavily optimized code. If we look at what we generate there, we see a different pattern in terms of the red boxes. First is the red box is much bigger, so you might think, cool, that's bigger, more instructions, less efficient. What's happening here though is that we're able to recognize that for loop can take advantage of very wide registers and vector instruction. And on the particular machine that we were using to do this test, it was using AVX2 instructions, 256-bit wide registers. The other thing is that we can see in terms of the red box, small red boxes, we're actually doing 4 elements per iteration of the loop. So the loop unrolling, but 4 times rather than 2 times that happened to C2 JIT compiler. The effect of this is that now, rather than processing 2 elements per iteration of the loop, we're processing 32 elements, and for each of those 4 times loop unrolling, we're doing 8 of them in parallel. So much, much more efficient in terms of the code and the overall performance that you will get for the same piece of code. So what we end up with is a situation where we get a compiler that generates faster code. And this is just some benchmarks we did on some fairly standard pieces of software. Things like Cassandra, 22% faster. Things like Pasta, nearly 40% faster. This is all really good. So you think to yourself, right, that's the answer. We'll just use that. Everything is great. Except that everything has a cost, doesn't it? There is no such thing as a pre-lunch, even the one that we're about to have after the session finishes. So there is a reality of better JIT compilation. Better JIT compilation has cost. What we need to do is we need to spend longer generating code, processing that code. We have to figure out how to make those optimizations work. And what that leads to is more time on the wall clock, more time in real time to compile our code. It also is likely to require more memory to do that work. Now, if we have a nice big powerful machine, if we're running on, let's say, 64 V cores, then we're probably not going to be too worried about that. But if we're running on a container that only has 2 V cores and a limited amount of memory, then we could run into a situation where we're using all the V core processing power to do our compilation, and that means that we're not processing what the service is supposed to be actually doing the application. Similarly, we might find that we run out of memory, so we get out of memory errors. So we end up with a trade-off between provisioning more resources for the containers that we want to run our service in to handle the extra compiling, versus the performance we're going to get overall to generate better throughput for those services. So it's a bit of a balancing act. And if we look at, again, some more graphs here, so hopefully you can come and see this. What we've got here is running a simple application service in a 2 vCore container. This was using Hotspot, using the C2 JIT compiler. What we see here is, again, like that graph that I showed you earlier, we've got that starting off slow. In this case, it's getting to its optimal level of performance really quite quickly, and then a nice stable level of performance. The bottom line represents the CPU utilization. And during the first part, what we're seeing is compilation. That's compiling all the code that we need to do the work. And so we get very high CPU utilization, and then drops down as the application is now doing work of the service itself. In terms of provisioning, what we're having to do here is provision 2 vCores to deal with that first part of the application startup. But once we drop down there, we're actually only really using 1 vCore. So we've doubled the number of vCores of provisioning in this service just to handle that first piece of work for compilation. Let's do the same thing if we use our Falcon JIT compiler. That looks very different. So what we're seeing now is that we have a slower warm-up phase. And if we match that against the CPU utilization at the bottom, what we're seeing is that the CPU is that the vCores are completely maxed out whilst we're doing this compilation. It's taking us longer to figure out the optimizations that we need to get those optimizations into the code that we return. And then we're also seeing that there's ups and downs in terms of the performance. And that's because we have more de-optimizations. We've taken assumptions, we've used more extreme assumptions about how the code is working. Some of those have worked out to be false. We've had to throw away the code and recompile. And we can see that, again, that matches on the bottom graph, where when we've thrown away code because of the optimization, we've had to recompile it, which then pushes CPU utilization up again. But the good thing is, obviously, when you look at the far right-hand side of the graph, we still have the same CPU utilization as we did before, so we haven't increased that for the same number of transactions per second. But we have got throughput to be higher, so we've actually been able to do more transactions per second than we could do before, even though it's taking us longer to get to that point. So then, this is where we come to the cloud-native compiler. What if we take the JVM and remove and decouple the JIT compiler from the JVM itself? We don't really remove it because we need to leave it there in case the cloud-native compiler is inaccessible. But we can turn that into our cloud-native compiler and introduce the idea of JIT-as-a-Service. Well, why would we want to do that? Obviously, there are a number of benefits to that. Speed is one of the most important of those. We can reduce the memory footprint, we can reduce the warm-up time, we can improve efficiency, we can have write side. But ultimately, what this all equates to in terms of a cloud environment is cost. Because if we can reduce the number of vCores we need, if we can improve the number of transactions per second that we can handle for the same set of resources, then we're going to reduce our cloud bill. And cloud is all about utility-based pricing. Less resources we use, the less we pay. So let's go back to our graph here and overlay from that the idea of using an external JIT compiler. So we'll take Falcon, the blue line, and move it into a centralized JIT service. What that now looks like is this. And if I drop the blue line out, make it a little bit easier to see, we've got essentially the same profile that we had before with the C2 compiled code. So very fast startup, but no worse, no better than C2 in terms of the speed of warm-up. But we get to the optimum level of performance, which I'm guessing this graph is probably somewhere in the range of 15 to 20% better almost immediately. And then if we look at the performance in terms of CPU utilization, we've effectively eliminated this section at the beginning where we need to do all this compilation and we need 2 vCores. So we could, in this particular situation, probably have reduced that to a single vCore and still got improved level of performance out of the same piece of code. So half the number of vCores, but we're now getting 15 to 20% more throughput than we had before. Of course, you'll think about this and you go, well, okay, so you're moving the JIT into a different service. Aren't you just shifting the cost? Because now I have to provision a cloud instance in terms of putting the JIT into the service and have a cloud instance for that. Well, yes, it does, but you're shifting it to a more efficient place. Because what you can do is you can provision a bigger number of V cores if you want to, and that way you can have the code generated more quickly. But there's other things that we can do, because now we're running a service that's long running. What that means is that when we start up our microservice and we need to compile a particular method with a set of optimizations, we pass that to the JIT compiler. It does exactly the same thing that it would do if it was locally. But if we start the same service again, and we need to compile the same method with the same optimizations, when we request it from our centralized service, because it's been running, and it already has that code compiled, it's cached it, we don't need to compile it again. We simply return back the method that we passed before with that compiled code. If we start up multiple instances of the same service, the same thing applies. We can simply return the same method of the same compilation to the service and take advantage of the fact that we're running as a separate thing. So in terms of the cloud-based compiler, we end up with, like I said, this JIT-as-a-Service. We can make it elastic. So again, we can shrink that down. Once we started up all our services, we could reduce the number of resources being used by our JIT-as-a-Service while still maintaining the idea of the ability to pass back cached instances of methods. But there's more. Because the reality about application code is that the vast majority of our code is going to execute more than once. So if we want to run it on multiple devices, we're using services, we want to restart those services, we want to run multiple instances of those services. When we do that, we're going to find that we have a common set of profiles for the behavior of those services. And even if we're dealing with rapidly changing applications, it's still going to be the same thing. So this is where we take advantage of that caching. So we can reuse the code even with respective optimizations. What it allows us to do is to use that idea of a unit. And the way that I kind of refer to this is more like a fingerprint. And we can use, in effect, the sort of like Shazam approach, which is where we say, okay, here's the method, here is the set of profiling information that we have collected for that method. Match that against what we have in our JIT compiler as a service at the moment. You match against that and go, yes, this is a set of compiled code that will match against that, and we can return it to a particular JVM. So on the right-hand side here, we've got 5 different JVMs. What will happen is that 3 of those JVMs are passing the method that they want compiled with the right set of speculative optimizations. So they will immediately get back that compiled code. The other 2 are passing, let's say, the same method, but because it doesn't have the same set of speculative optimization profiling data, we can't immediately return that to those JVMs. We will then compile it, pass it back, and store that locally. So we'll have multiple instances of the same method compiled, but with different speculative optimizations. And we can then match against those as we need them, and then deliver the right code, which gives the right level of performance. Again, if we're just shifting the cost, this is where we see the ability to reuse code that they've already compiled makes a big difference in terms of reducing the amount that you need to spend on our JIT-as-a-Service. So really what we're doing here is we're saying, okay, so take our cloud-native compiler, use the advantage of that so that we're not compiling the code every time, we're not compiling it locally, we don't need all of the resources that we need to do that compilation, we can shift that away, we can reduce the resources required for each individual service. So to summarize this, essentially, cloud-native compilers, it's saying to ourselves that decouple the JIT from the JVM, take advantage of the fact that we can use better resource utilization in terms of the JIT as a service, we can provide better optimized code. And one of the things that we're experimenting with at the moment is saying, okay, so you pass us a method with a set of profiling data. We will compile that using our JIT-as-a-Service and generate optimized code, which we return to you, exactly as I've described. But what we're going to do is we'll say, well, there's some optimizations we think we can use for this method and this set of profiling data, but they're going to take a lot of time to actually work through and make sure that we can generate even more heavily optimized code. So having returned one version of that compiled method, we'll then set about using the resources we have within the JIT-as-a-Service and generate that more heavily optimized code. The next time a service requests that method with the same sort of profiling data, it gets the even more heavily optimized code. Or we could even preemptively tell the JVM, actually, we've now got a better version of this. Do you want to use it? And we could pass that back as well. So there's a lot more we're doing in terms of the research on that. What this leads to is improves warm-up time. So you get much faster startup time or warm-up time than you would with using a local JIT compiler. There's a lot of things going on there. Now, if you're interested in trying this out, you can do it for free. We have what are called stream builds of our platform prime JVM. So if you go to our Azul website and go to products, find the stream download, you can download it free and try it out and see what you think. And that is that. Thank you very much.